Good evening, everyone. I'd like to welcome you to yet another Nano-EP seminar. It's my distinct honor and privilege to welcome Professor Wang from Georgia Tech. He's in the School of Material Science and Engineering. He got his PhD in Arizona State, and he's got a number of honors. He's done a lot of work in the fields of oxide nanobelts and nanowires. He's made contributions to synthesis, discovery, and characterization of these different structures. He coined and pioneered the field of Piezotronics and Piezo-phototronics, and he's got fellowship from MRS, APS, AAAS, and won a number of different medals. And so I could go on and on. I could spend the entire time talking about how distinguished he is. So it is my honor to welcome him here today. He's going to talk to us about nanogenerators and piezotronics from fundamental science to novel applications. Professor?
Thanks, Josh. And it's a great pleasure to be in UIUC. My last visit was probably 8 years ago. I can recall I visited mechanical engineering and I gave a talk. And I cannot remember what I was talking about there, but I hopefully give you an update report of what we are doing today. And there's two key words about this talk. Mainly, one is related to energy, the other related to sensors and electronics. 5 topics I'm going to cover. Number 1 is the nanogenerators, update progress. Next one uses nanogenerator as a power source for power some systems. Third, use nanogenerator as an active sensor. I'll explain to you what do I mean by active sensors. Okay? And lastly, I'll talk about the Piezotronics and Piezo-phototronics, and these are some new areas we have been developing in the last 6 to 7 years. Can you hear me on the back? Okay? All right, I'll try to speak loud. The motivation we do this work is mainly utilize the energy available in our living environment. Okay? I hope the microphone works too. Okay. The applications involve small electronics, small devices, and back to 7 years ago, we worried about that. How do we power these small devices and use for a variety of purposes? For example, if you use a sensor network, you need small sensors that can sensor and send a signal wirelessly, and also is distributed around our environment over a large scope and a high density. So the key question is that, how are we going to do it? So we thought about that time there's a number of ways to do it. You can use the solar energy, thermal energy, and other energies. The way we start is use energy from human body. For example, we look at the energy associated with our daily activity is substantial. So that's the starting point. And can we convert this tiny mechanical energy into electricity? So that was the motivation, and we started this one 2005 and up to today. So I want to give you an overview. What we have been doing in the last 7 years. Nanogenerator has been achieved by a number of effects. Number 1 is piezoelectric effects. Number 2, triboelectric effects. And number 3, Photoelectric effect. I'll give you an overview of each of this one and give you update progress. The original inspiration for our work came from these early publications that will use an atomic force microscope and to mechanically deform a single nanowires, because this is a piezoelectric. So piezoelectric can generate a charge that can drive electron flow. And that time we detect 5 to 10 millivolts of output. But we kept our dream because that time the output was rather small. We continued on this one improvement. Up to today, we can utilize for a number of purposes used to drive conventional electronics. 3 things come from this work. 1 is the terminology of nanogenerator. Number 2, self-powered nanosystem. We will not only make nanotechnology, we will make this self-powered. And number 3, from here we derive new electronics, which I will describe. Fundamentally, it is related to crystallography. When you grow these nanomaterials, each is a single crystal, but crystallography structure is, for zinc oxide, is the Woodside family. The Woodside family is a non-central symmetric. That means the cations and anions are tetrahedral coordinated. In such a structure, when you mechanically apply a strain, the shape is being distorted. As a result, the center of cations and anions has a polarization. So each unit have a polar direction. The whole nanowire has a macroscopic potential inside. This is because at the two ends we have polar charges. The polar charge produced by piezoelectric effect. How are we going to use this? The reason we use nanomaterials, it can be easily triggered by small mechanical force. For example, if we connect to an external load to this, apply mechanical force will produce a piezo potential. And this potential will drive the electron to flow. Why the electron has to flow? The electron has to build an opposite field to screening these charges. That's what the electron has to do. But we purposely build a blocker, a Schottky barrier or insulate layer here. So electron flows, or electron accumulate over here. So that's the basic idea. The piezo potential drives the electron to flow. If you draw in the Venn diagram, it looks like this. If I have a single device, single wire device, put on two ends bond, and the substrate bend inward, produce a pure tensile strain. The reason because the thickness of substrate is a lot larger than the thickness of wire. So this wire is minority in this whole system. When this piezo potential produced, the electron tends to flow. But here is a Schottky barrier. And the Schottky barrier will hold the electron around here. So the electron flows to balance the Fermi level on the two sides. You see the first output peak, and this is the first signal, then reach new equilibrium. And once this is released, the electron flows back from here, and because the Fermi level difference, the disappearance of piezo potential, give you another peak. So if you do this cycled deformation, this different back and forth, you see the electron flows in, flows out. Very simple. Very simple, okay? So this is the basic principle of this one-wire-based generator. In the last 7 years, what we have done, what we just talked about with you was around here. At the very beginning, we create the idea, but in the last 7 years, we went through all the steps to bring you to the maximum output today. Instead of giving you an overview of all these details, let me show you what we can do today. Then you can think, how can you apply for your purposes? Okay, so let's look at what we can do today. This is a device. This device is a package. Inside is one layer of this vertical nanowires. Okay, and each of this one, once you mechanical strain by your palm, they can give about 50 volts. Each layer can give 50 volts. All these 9 put together is give you a maximum of the current, about 100 microamp current. Okay? So when you put this together, it's as a power source, and then you use the one to trigger biological species. This give 50 volts and connect to the nerve of this frog leg. You can see this frog leg jumps. It's not mechanical vibration. It is the electric stimulation. Okay? Stimulation. Shows this one, this is the output we can reach today by this nanowire-based devices. From 5 millivolts to 50 volts, we took about 7 years to do that, okay? But it's possible. The second effect I'll talk to you is Triboelectric effect. This is well known. We knew this one when it was high school, middle school physics, right? One material scrub against the other one, you have charge. What's new about it here? Let me show you what we have done. Use this effect. It's a simple, easy, and high power output. Okay. First, look at this one. These are 2 pieces of polymer on the surface with some nanostructure introduced. You see the electrode here. When you mechanically deform this one, we have a voltage, a few volts output. Okay. This is no piezoelectric material, but this is just relative sliding one polymer against the other one. What we used to know is that Triboelectric give you charge. But this charge, how can make this charge and produce a potential to drive the electron to flow? That's the current, that's the power output. So let me show you the principle in a second, okay? So we have 2 pieces of polymer, for example. One is the gain electron, one is the loose electron. When they are physically in contact, if they're slightly, relative sliding, there's a charge transfer. Make one positive charge, one negative charge. We know this one for a very long time, centuries, okay? Now, if we know this one, if you use the surface features and purposely keep a distance of the two charges, so you have a distance separation of the charge, you create an open circuit voltage. Experimentally shows this. Okay? When this voltage is created, if this is connected to external load, the electron tends to flow to build the opposite potential to cancel this out. So this electron flow through the external load is the current you observed. Okay, this is the current. Once you release it, it's fold over, and the gap disappears, the potential disappears, electron flows back. The integrated area are the same because the total charge flows in equals that flows back. And the key here is that you have to find a process to make this separation, which typically need a separation about 10 to 50 micron distance. So you have surface engineering, and this happens automatically when you do the mechanical separation. Okay, so that's the idea for this principle. And excuse me.
Any reason why it's asymmetric?
You mean this? Okay.
The peak is much.
Yeah, because when you press it and you release, the rate is different. The rate is, if you have a symmetric compressed release, you should see a symmetric peak. The reason here is that you don't see that when you press it, you release it. Release could be a little faster, so the peak is higher. Okay, but the total charge remains the same. Yeah. Okay. So this is the why. So you have a number of steps involved in this, right? Okay. What are the choice of materials? Can be very diverse. You just need to choose one material to use the loose electrons, one material use the gain electrons, and you put them together, they can produce electricity. Okay? So the whole idea is that choose two different materials, and they are very far apart in the Triboelectric series, and they can do the work. Okay? And of course, you can through the surface engineering, you can do the patterning, use the lines, this square-based, pyramid-based, and you can increase the output. You can make it completely transparent and put on the wafer, etc. And you can see with the features introduced, the pyramid introduced, the output voltage increased by a factor of 4, and current increased by a factor of 4, and etc. You can use a lot of surface modification to improve it. Okay, and up to today, what's the best we have achieved? The best we have achieved is 1,000 volts. I didn't show you here. The reason was that we just got the data a few days ago. But here's 200 volt. Okay, see the 200 volt, and the current about 100 micron. If you optimize the load, the output of a fingernail size, one layer, can give you 8 milliwatts of power. That's not too small. Let me show you. This power lit up LED simultaneously, a bunch of LEDs. Okay. So you can see that this is used for finger tapping. You're going to have about 40 or 50 LED being lit up instantaneously. Okay. So then there's another one with the letter of Georgia Tech GT show up from this one. So what I'm talking about, tiny physical motion. You don't have to be gigantic physical motion to produce this one. This one can be by muscle, by your typing. Let's say put this under your keyboard. Just keep typing. You can generate electricity feedback to your PC. It is possible. Okay. It may not completely dry the PC, but can make your battery last a little longer. Right? The best today, use a size about 5 by 5 centimeter by that size, and put on the foot, simultaneously lit up with 600 LEDs. Let me show you the video. See here? It is substantial, right? It's fairly large enough for this. If you can put this stack together, one layer, multi-layer, one stack, multi-stack, put in your shoes, walk on campus, you get your phone charged. Is this possible? I will show you it is possible. And this is the soft power ideas we proposed a few years ago. Now that we have an energy harvester, energy storage, sensors, data transmissions, and all these things can work together. I will give you one example. This is an environmental sensor for mercury detection in water. We can use the electricity generated through the water flow and detect the mercury content. If exceed the limit, they send a warning signal out. Okay? So we have a number of examples to show this one. It can be a system to work independently by itself. So if you put an environment, you don't have to fish this back. It can use the energy environment, generate electricity itself, and detect the species you want to detect, and also send a signal to a central receiver. That's what we want for the sensor network. Okay. Here's an example, a commercial temperature and wind speed sensor. We use our Nanogenerator charge this lithium battery, and it can drive these two sensors. This is commercial. Okay. Then indoor, this is the receiver. Both are 50 meters away, and this can send a signal in, and the inner door can receive it. So therefore, if you have a commercial system, we can use this as a power source, integrate with the parts you have, and put in an environment. You don't need to charge the battery or replace the battery anymore, because this is good for what? When you measure this one, a lot of things can be generated from this kind of motion. So the other one showed a cell phone charging. This is a cell phone. First one is use a cell phone to completely drain the battery. Okay, completely drain the battery. Then use our Nanogenerator to charge the battery. Put back in, it can dial. Okay, and this is why I show you that if you make this into stacks, into multi-layers, put your shoes, charge your battery is not a dream anymore. It is very visible. Okay, here it is. It's a little in a lab, dirty work, but it works anyway. So this is what they're going to do: charge the battery. It's a commercial battery here, and of course they use a little machine to trigger the Nanogenerator rather than use a finger tapping. They take a long time. Okay, so after charging, and now they gonna put back in. They call this phone, see if it's waked up or not. Okay, it's a little longer video, but let me show you. So they're going to dial this phone. Turn it on. 404 Atlanta area code. Hopefully the other one wake up. It'll wake up. Okay, receive the call. To show the concept that you can truly charge a cell phone. It's not a dream. And of course, we need to charge it. It can run for 30 minutes, but we can improve the design. They can do that next year, right? But so we had a dream 7 years ago. When I draw this slide, 2007, I said we want half the energy available around us, but we waste them all the time. Can we power things like this? So today we already reached here, and the next target is something towards this. Okay, so that means small electronics don't have to be extremely small. Something viable we use every day, portable electronics, and we can dream big because we have a lot of students here. I like to inspire our students to think big. The reason because years ago, when Faraday was first proposed electromagnetic induction, he probably did not think this can make giant things like this. Right? It was just effects. Well, if we can make this cheaper, high power output, we could harvest energy from all these places. Right? This is not a dream anymore. Or to show that, put on the highway and put under the inside the tire in a cloth, maybe waves. Okay, we need to figure out a way how to do it, but it's a possibility. It's a dream list, and again, this need if you can make it cheaper, better, and greener. Okay, so the material use has to meet this criteria. If you particularly use the larger amounts, you have to consider about that. So this is the think big pictures. The second topic I'd like to bring to you, hybrid cells. We use solar cell to harvest solar energy, thermoelectric, harvest thermoelectric energy, and chemical and mechanical. But can you use one device harvest both type of energies, which we call hybrid cells? We developed this one 2008. Up to today, we have number one. I'll give you one example. This shows the harvest the thermoelectric energy and mechanical energy through body motion. Okay. The design is like a traditional. For example, this is the thermoelectric part. Use the standard traditional materials, and this is the nanogenerator, piezoelectric nanogenerator based on top. This halves the muscle stretch movement. This halves the energy from body temperature with the environment. Okay, so the design schematic show here, and this is a video. It's not a fancy video. This is my postdoc Simon Lee. Simon used the hands hold this one. When he releases his hands, you can see the voltage going up. That's the thermoelectric part in work. Okay, and this one shows the mechanical part. So when he's stretching his fingers and he has the muscle movement, this gives you the AC output. The piezoelectric generator gives you AC output. The thermoelectric gives you a DC output. So if you put all this together, then two technical complements. Thermoelectric gives you high current but low voltage. Nanogenerator gives you low current but high voltage. You can see in the current is the thermoelectric dominant. This is the AC part. In the voltage, this is the nanogenerator, but the thermoelectric generator is very low voltage. So both complements, but it can't work together. And this video shows you it can work together. Oops, sorry. The reason I show this one is just show you that there's other way you can do it. One device has one type of energy. You can divide multiple devices integrated together. And today we can do one device, integrated device, have three different type of energy: mechanical energy, thermoelectric energy, and the solar energy as well. So just use whatever is available. Use whatever is available at the device, whether it works. Okay. Anyway, so this shows a concept. Now I want to show another important application, because a lot of students work on sensors. Most sensors are passive sensors. That means if you apply the strain, the resistance change. You apply voltage, you measure current, you know, and there's a resistance change. This is passive. But if you use nanogenerator reversely, they give you a signal as you apply the strain. You can sense it. Let me show you a few examples here. Okay. The first example is this one. This is a single carbon fiber. On one side, we made a biofuel cell, convert glucose energy into electricity. The other end is a nanogenerator, convert pressure change into electricity. So if this is the power source powered by glucose, this will be the sensors for measure the pressure change. Reversely, if you keep the pressure change to be a regulated manner, this can be the power source, this can be the sensor for glucose. So let me show you the example. This keep the glucose the same, but the pressure changes from ambient pressure 5%, 15, 35%. You can see the output electric signal scale linearly. No power was applied to this. This is just power by itself. Okay, so this is one concept: self-powered blood pressure sensors. Hopefully, in the near future, we're going to develop this one. This is a vibration sensor. You know, when you have a vibration, you want to detect it. Normal way is shining a laser spot and detect it. Okay. Here is the one. If you have a cantilever, you put a nanogenerator right here. So when this thing vibrates, the strain at here will produce a oscillating voltage. So you can output the voltage here. This gives you the frequency of the oscillation, also give you the damping of the entire thing. Okay? So this one can use for infrastructure monitoring, for example, like a bridge vibration or even earthquake. So this is self-generated electricity, can be a signal. If you have a drum surface, recently we have a drum surface, we'll put this one, the fingernail size nanogenerator on different positions. So you knock the drum, you can detect different frequencies. The reason because at the center here is mostly the base mode. This is the second, the third mode here. So if you put a laser spot here, you may not detect this mode because their mode, the vibration amplitude for their mode is minimum over there. So this is for vibration detection. Vortex, air, gas, or liquid flows you generate vortex. You can design a structure inside the pipe. When the vortex, this oscillation, we do the simulation here, and the oscillation frequency give you the flow speed of the liquid through here. So this is an indication what is the flow liquid of the inside here. Okay, so you measure this output voltage, you know the flow. If you have a water pipe, want to monitor that, you just put this in. You don't need other power source. You can do that. Okay, so this is the other one is the pressure sensors. We made this here. You can see the water droplets on the surface here each give you output voltage here. Okay, and this is the feather. You put the feather on, you generate a signal, and if you plot it, they give you a signal like this. This is the front end to touch it. This is the bottom end to touch it. Give you the dynamic process of this feather touch it. Okay, so not only can sense, give you the process. It goes on the surfaces. So this is a self-power sensors here, and this thing can be expanded a lot more. Okay, skin sensor. Smart skin. You can put a ring here. You can see here the electric signal here. And if you analyze the signal shape, you can detect it. And I propose this one for driving. You know, when you're driving, you feel tired, your eyes start blinking, and then we should build an electronic. Say, okay, you should stop. You should take a break, right? Because when you normally, your eye blink differently when you are really tired and ready to sleep, right? So could be a possibility to detect that. Right? Just another possibility. So this you can think over for a range of active sensors, right? So that's first part of my talk: energy, nano energy, particularly energy related to small systems. Small system. Now I want to switch our idea a little bit. Think about electronics. This is related to electronic engineering and W students here. Okay, what is the basic idea? What is the motivation? And we have a lot of people working on electrical engineering. The goal is make it smaller and faster. But in recent years, there's a huge market on personal electronics, portable electronics, polymer electronics, inclusive Piezotronics. Professor John Rogers' group is the leading group in the world making Piezoelectronics. Sensors are accurate. If you integrate this all together with the speed, you can drive this in a different angle. It can be 20 degree or 70 degrees, depends how you define it. So this is I think is a lot of other things can be done. So functionality is what we need. What kind of functionality? Let's look at the prediction from Scientific America. They say that in the past, what has driven us is miniaturization, portability, and function. From vacuum tube to solid state, from mainframe computer to desktop to cell phone. One each person. Used to be a few per country, maybe. So what's next? You think what's next? It's going to be smaller, and number going to more. So therefore, we have to think, what's the next one? And Scientific American predict is like a health monitoring, the brain computing, and wallet and skin. I don't know how to achieve this, but this is what they predict can change our life. And when you shook a hand with somebody else, your balance transfer. Okay, it won't happen, I think. But somehow more than that. But anyway, it's related to human. Related to human. That means communication between human and electronics is a vital part of future market electronics. So that means that we need to interface us with electronics. How? Well, keyboard, yes, it's one way, but a variety of other ways we have to do computer interfacing, electronic signature, not only record the graphics, but record the pressure or force or the speed at which you sign your name. And nanorobotic, we already predict this can go to bloodstream to clean up the cholesterols and make you healthier. But so far, it has not happened yet. Okay? Because a lot of complications. And this is also from Professor Rogers' group's work. And electronics, something you can make really flexible. So how do we interface us with silicon? Is this the way you're going to interfacing? Well, maybe not. But so because this is electronic communication and this is the mechanical sensation, and through two processes. One is electrochemical, the other is mechanical. Electrochemical process is a nervous system, but mechanical is the other one. Mechanical system is very general. For example, when I talk to you, my voice is mechanical, vibration. And the other one, when I talk to you, you can see I'm very happy to see you today. Express my surfaces, my face, through visualization, through my muscle motion here, okay? How are we going to do that? We propose a way to do it. I just talked about that using piezo potential to drive electron flow in an external load is the basic principle of this piezoelectric nanogenerator. This is the way to do it. You do dynamical straining. However, you can do a different way. If you strain these materials and hold it, the piezo potential preserved because the ionic charge remains at the end surface. And this change at the interface can largely tune the transport of the carrier. So therefore, when you make the carrier P-type and N-type go through the interface, the piezo potential can affect its transport. So use piezo potential as a gate voltage to change the transport of these carriers inside the circuit is Piezotronics. Okay, so this is the idea. Let me show you, is this possible? The first time we faced this one was 2006, 2007. We call nano Piezotronic. Today we don't call nano Piezotronic. The reason we dropped the nano reason, this is also in the thin film and other materials have this effect as well. You don't have the nano to have this effect. The only thing is that when you get nano, it gets larger. What's the difference? Famous picture is here. Source, drain, and gate. The gate controls the channel width. So you control the channel width, the carrier flow through here being controlled. Can we do the change? Let's say if we use a flexible substrate, introduce a mechanical strain. Mechanical strain produce piezo potential inside. And then if the potential can tune the junction between the metal and the semiconductor, when the carrier flows through here, it can control the current. So this is through channel width, this is through interface. This have 3 terminal, this have 2 terminal. And this is probably a hard substrate. This could be a soft substrate. You can switch the strain from tensile to compressive so you can control the right-hand side of the devices. So this is the ideas. Does this work? Does this work? Let me show you the example. It truly works. The first one, let's make a single device on a polymer substrate. This is the device itself. And you apply the strain, apply this. Because on polymer substrate, you can simply apply the strain. Then you measure the transport. This is the transport property here. Okay? If you fix the source strain voltage, replot this, you get this. This is the strain applied. This is on the tensile strain, it is on. Compressor is off. Why? There's a switch effect here. Used to be this is gate voltage. This is gate voltage, but now it's a strain. Why is so? Is in such a device here, besides the voltage we applied, this voltage offset the Fermi level by a difference here because the bias applied here. Besides this external voltage, there's an inner crystal potential. Okay? When you apply the strain, Piezoelectric produces an inner crystal potential. Now, the electron flow this way. So if this is a positive piezo potential, it lowers the barrier height, so electron flows easier. This is the effect you see. The larger this potential, the easier it flows. Reversely, if you compress from tensile strain to compressive strain, this is the lower piezo potential side. It erases the barrier height, prevent electron flow this way, cut it off. This is what you see here. This on-off ratio is going to be about 500. Okay? So you can use this as a switch. You can make a logic computation. Logic computation. This logic computation is not controlled by voltage as we used to do, but the strain applied to these devices here, and this is the structure I will show. And my student Wang Wu is the expert on this. So show the basic logic. You can do this, and I think this can be further put on the skin. If your skin move this way, the other way, it can catch the signal. Okay, use the skin motion to control the logic computation. Okay. Vertically, recently we not only make lateral, we make vertical ways. Vertical way is that you can. First one is done by AFM. You can put the AFM here. You can apply the mechanical strain step by step. The piezo potential increases, and this move the AV curve to higher voltage, turn-on voltage here. So this is use the piezo potential to shift the turn-on voltage to a different value, put the strain applied here. Here is 2 leads. no third lead here. And recently, my group also students made this into not only one, make into a 9,000 array. Make this 9,000 array as transistors. Each of them can be individually addressed. And this change is different from the traditional ways that traditionally have applied gate. This occupies space. If you have such a density device, where are you going to put the gate? So there's a different way to do things through this. The key idea is this potential modified interface contact. They control the current. So there are different controls, but same purpose, and the transistor is control of current through this way. What's the difference of this piezotronic effect from piezoresistive effect? We are very familiar with this. Carbon nanotube, silicon, use strain sensor, use this one. This is a linear IV curve. This is a nonlinear rectified behavior IV curve. This is symmetric. That means what? It's a resistance. That if the resistance electron flow this way or electron flow that way, it's the same. There's no polarity, but this does. Because you raise the barrier height here, you lower the barrier height here. This have different effects. This is a volume effect, and this is the interface effect, because right here, the polar charge actions here, all right? This is no switch function, this will have a switch function. Those are different effects for piezotronic effect. What happens if you apply light? When the photo energy is more than the band gap, what changes? Let me give you a couple examples. Let's do basic. If you have a metal semiconductor contact here, and this is the simple band diagram here. And now, if you apply a strain to this, the strain produces a polar charge due to piezoelectric effect right at the interface here. And if the doping in a semiconductor is moderate, so if you over-dope it, there's no piezoelectric. If you under-dope it, the semiconductor property will be limited. So you have to be a moderate. We found a 10 to the 17th percentage tube is the moderate doping for that. Okay, let me show you. If this is the case, even you have some doping, the doping will not completely cancel this ionic charge, but partially screen. This is ionic charge. It will not flow, only present at the interface. If you apply strain, it generates is present there. Okay. In such a case, it will lower the barrier height for tensile strain. But if you compress the strain, the negative ions raise the barrier height. What this has to do with my device? Let's look at the band diagram here. If you use the photon, excite the electron hole pairs. If you introduce negative ions at the interface, you raise the barrier height too much. Accelerate electron separation, but could trap the holes. So this is favorable electron separation, but not holes. But if you use this ionic charge, lower the barrier height, and decelerate the electron separation, but could accelerate the hole separation. So in reality, these two cases have to be optimized. And we found this case. You see, this is the sensitivity of the detector here, and found only at a particular strain, its detector reached the maximum. Because the barrier height at this is the best performance, give the best performance. If you have a p-n junction, this is p-n junction here, same thing. If you have a local ionic charge introduced by piezoelectric effect, they give you a little dip here, and this could be trapped electron momentarily and could enhance LED performance. If you have a negative ion, give you a little bump, and that can also affect the charge recombination or separation. I will use two examples to illustrate you this one. One example is the solar cell. One is LED. One requires charge separation. The other requires charge recombination. First one is solar cell. If you use a single cadmium sulfide nanowires, copper sulfide as the shell, this is the P type, this is the N type, p-n junction, co-shell. And we use microscopy to prove it is the case. If this is the solar cell, if you measure the solar cell performance, you get this. It's not the best solar cell at all, but I want to show the effect. If you apply the strain to this, do nothing, just apply the strain. Look at the photo current. Increase from 0.25 to 0.32. 40% increase. The voltage remains almost no change, a little increase. That means what? you increase the strain. You made a solar cell, you do nothing, you just apply a little strain. The efficiency increase by 40%. That's a good thing, right? So you just make the device, apply the proper strain, package it, and leave it the way it is. What's the reason? The reason is because we have ionic charge at the interface. They change the barrier height for the electron separation. So easy for the electron to transit from this side to the other side. You can have charge separation here. So that's the simple reason for this. The second example I give you is LED. I skip this electrochemical process. Well, this also can enhance electrochemical process. Let's look at LED. LED is charge recombination. And if you have a gallium nitride, P-type gallium nitride, you put the N-type zinc oxide on top of that, and you apply the proper strain here, and look at the emission light. Emission light here, you find without apply this Piezotronic effect, with apply the Piezotronic effect, the emission intensity has a factor of 17. The absolute efficiency has a factor of 4.25. Not 4%, it's 400%. So this is gigantic enhancement. This is for the LED. Why is so? Why is so? The reason is because we suggest that if you have a gallium nitride side, zinc oxide, at the interface, you have ionic charge here. The ionic charge produce a local dip in the band diagram. So when the electron move here, they could be temporarily trapped for a little longer, enhances the electron hole recombination rate. And this can contribute the emission of the photons. Okay? Recently, we have done a lot more work on this, not only applied to this nanowires, also applied to thin film. If you have a thin film, this can also enhance the emission as well. So we believe it's a rather general phenomenon. You see, just ionic charge tune the band can enhance the recombination. This is the Piezo-phototronic effect for the LED. I focus a lot on the zinc oxide. Many people know I work on zinc oxide for 12 years. And we're probably the longest group working on that for 12 years. Very stubborn. But this material is really unique. But the concept I introduced can expand to many materials. It's not only the zinc oxide. We find can expand to all these materials. But if you look at periodic table, this is the periodic table. Those are materials for the 2,6 compound seminar. Those are the materials we have done. We have used for this purpose. The other materials we have not used. The reason because we don't have the sample. If you have the sample, fine, it should work. Okay, and so the materials system is really broad. Okay, the idea is general. So the 2,6 compound for 3,5 compound semiconductor, we have done this. Another group in Taiwan has done indium nitride, and those materials should work as well. So Woods-up family, zinc bromide family, all should be giving similar phenomena here. So this concept, the piezo charge induced band structure tuning, could be general. It can apply for many other materials. So if you don't work on the zinc oxide, it doesn't matter. As long as you have this material have dual semiconducting piezoelectric property, you can try. Okay. So why people have not thought about this before? Okay. I think here could be the possible reason for it. In the past, optoelectronics is a huge area, and most of the materials are 3,5 compound semiconductor, 2,6, 3,5 compound semiconductor materials, and this is what we use here. There's another community use PZT, lead zirconium titanium oxide. Lead zirconium titanium is a material not very much useful for optoelectronics. So they focus on different materials group. But now if you use one material, bring them together, you have new overlaps. The coupling between semiconductor and piezoelectric is what we call Piezotronics. Piezoelectric electronics, we simply call Piezotronics. This is the triple junction area here is the photon, Piezo-phototronics right here. Okay, this is the basic physics. Why they should introduce something new, fundamentally change it. So what is Piezotronic effect? Use piezo potential to tune, control, charge, transport at the interface or junction. What is Piezo-phototronic effect? Is tune the charge separation or recombination at the junctions used in the optoelectronic process by this interface charge here. It's a one-layer charge, can do a lot of things for you, and I hope that can be new field, and that can be a lot of other people can study these interesting things, can find a lot of possible applications. What's the difference from what we do with silicon-based FET? This is voltage control. This is strain general inner crystal potential control. This is voltage governor. This is strain governor. 3-terminal, 2-terminal. Silicon-based materials, Wu-based materials. This is very fast. This is slow. And this is for computational logic and also for human-computer interface. We use for different applications. Both should be complement and integration, so we can put the two things together, utilize the speed provided by silicon technology and use the functionality provided by this one, because strain is a lot of functionality in this. How do you introduce that is another matter. Piezotronic transistor is a sensor, but it's much more than a sensor. Like we say, a transistor is a sensor, but much more than a sensor. But a sensor is not a transistor. This is the way to say it. The reason because this is what a sensor does. As a transistor, you have to have a switch function. You have the turn on voltage by apply a further parameter here. So with this characteristic here, so this is a new transistor for Piezotronic transistor rather than just a sensor. Okay, much more than a sensor. What do we look forward? Again, I also dreaming. From now to 7 years later. And this is the dreaming list. And this is what we're going to predict possible. For example, if we can develop this further, we can apply for pressure, imaging, and flexible electronics, and power source, touchpad. When you have a touchpad, you have this voltage generated, can be different way of signal transduction. And also smart signature here, and you record the force or pressure you applied when you sign your name. Smart gloves, when you build this around the finger edge here, when you move around, you can the kids can play game much more easy than today, rather than through the keyboard, right? So more dynamic. And if you use it for energy, we can impact the solar energy and the LED. And this can be also helpful for energy science. There was a group in China, I talked with them, they use this effect put on the silicon materials that can enhance the efficiency of solar cell or silicon-based in solar cell. So you can see a simple effect, more important, room temperature effect. If some effect is 70K or 50K, be a long way for us to apply. The reason, because how do you keep that temperature? That's a big issue. Room temperature effect will reach you very soon, because you don't have to cold or hot. Just what we live in can do it. And this is room temperature effects. Okay. So therefore, this is what my dream list. Let's see 7 years later whether we can do some of this or not. We check up back later on. Okay. So summarize my talk. A lot of cases, I talk a lot of things for sensors, LED solar cell. People can say, well, you do everything, do anything. And what's the focus? The focus is the fundamental physics and material system. The material we base on is like a zinc oxide or maybe gallium nitride and more. The physics use piezo potential. If you use this as a driving for electron flow, you get nanogenerators, and hybrid with other things, you can hybrid cell for harvest multiple energy, and the self-power system. All this is nano energy. The reason why we call it nano energy is the energy required for drive micro nano system, portable electronics. This is the possible application related to this. But if you use piezo potential as a gate voltage, you can produce new electronics, new optoelectronic processes here, and maybe self-charging power pack. I don't have time to talk to you about today. Piezo potential not only can drive electron flow, it can drive lithium ion to diffuse. Utilize this, you can build a self-charging battery. That means what? You put in your shoes, all this together, the battery, this unit convert mechanical energy to electricity and store it right away. They call it self-charging power pack. I did not call battery. The reason because battery you have a power source to charge it, but we use mechanical energy for this. So lots of other things to do. Of course, fundamentally, we can study at a scale here, low temperature behaviors. When you have a low temperature, I expect this monolayer charge, ionic charge interface, will play a lot more roles in a device functionality. So we're going to do that in the next few years, okay? So this is my summary, but the core is this. Use piezo potential drive electron to flow in the external load is the nanogenerator. Use the piezo potential to tune the carrier transport internally is the whole distance. Very simple, very easy. Okay. I'd like to thank many of my students, postdoc, and collaborate in the last 10 years. And today my talker, Sheng Xu, is here. Sheng was my PhD student, and he made a lot of contribution in nanogenerators. I thank all of them for their outstanding work. Again, I'm serving as an editor for a new journal, Nano Energy. I welcome you to contribute papers. Thank you for your consideration, and I hope this will reach an impact factor of 10 in a few years. Still look at the impact factor, right? But do contribute before they reach 10, but reach 10 will be hard. So get in first. Summary. Mainly 5 things. Number 1, nanogenerator. From the original concept, 2006, 5-6 millivolts, output current, picoambit current, almost no use. But today, we expand a lot and can drive conventional electronics. And what's next? We're going to commercialize this technology. We're going to bring to market, okay? Bring market this one. Self-power systems. Integrate with what we have now for a range of applications. You don't have to make a new product. If you integrate what you develop with some existing product, it's a new product, right? And active sensors. This is different from traditional sensors, right? Use this as a signal output. It's a sensor. It doesn't matter if it gives 2 volts output or 0.2 volts. It's a self-generated signal. They're called active sensors. Lastly, Piezotronics. I talk enough about this one. Piezo-phototronics here, and use this coupling effect. I can hopefully can build a lot of things. For students interested in this one, there's a free ebook you can download. All right, free ebook. Yeah. For this one, you can publish the next one in the spring of 2013. Hopefully, that can give students a better introduction of all the basics. Okay. With that, I thank you very much for the invitation. Thank you for the time. It's lunchtime. I'm sorry for holding you too long, but I hope give you enough information about briefly what we do. Okay. Thank you.
So, are there any questions? Great talk.
Yes, earlier in the talk, you talked about the idea of using the nano devices to clean up the blood vessels.
Yeah.
And you said it didn't work. So what might be the limitations of that?
No, it's, I didn't say it did not work. It's that one requires a lot of consideration. For example, first one, make sure you clean the right part. So there's a sensor unit in front. Number one, when you reach the part, like class we want to clean, how to clean. The third one is how can you power these things? This has to be electrically or convert glucose energy to electricity somewhat. And the third one is a system. Then let's say they have to make it really extremely small. It's too large. It can cause additional problem than the problem we try to solve. So there's a lot of people working on this nanorobot, but I have not seen that to reach that level yet. But hopefully, in another 10 years we'll reach it. But 10 years ago when the nanotechnology first came in, they said this can be possible in 10 years. This is already 20 years past. We have not seen that in reality yet. But keep hope. There's a hope.
So you showed the video using a nanogenerator to charge your cell phone. How long does that take?
How long take it? This one, this depends on the size of the one. What we use is only a fingernail size, 1 layer. So it took a few hours to charge that. We said, well, that's too long. But let's say we make a nail size, make 10 layers. 1 stack, make 10 stacks. So 10 by 10 is 100. So you can shrink it from 10-hour charge to 1 hour charge. So in that case, you can optimize that. We have not done that yet, but it can be done, I believe. at least you can do it. Regardless, turn on for 5 seconds or 1 minute, it can do that. Just you can integrate, you can improve.
Regarding the multiple material systems, do you see any of those materials as potentially generating more power than zinc oxide?
Very good question. We tried all this material. We tried the traditional PZT, barium titanium oxide, zinc oxide, also tried gallium nitride, and let's compare PZT with zinc oxide. The PZT has an outstanding piezoelectric coefficient, so it's outstanding for sensitive transducers. But we use the reverse effect. The power output is proportional to the square of the piezo coefficient, but the inverse proportional to the permittivity. The PZT has a large permittivity, so d squared divided epsilon almost cancelled out. So in that case, the power output is about the same as zinc oxide. So we consider it easy. For zinc oxide, it's very easy to fabricate. 85 degrees C, chemical synthesis, Zhong is the expert on for that. And it is environmentally green and biologically compatible. So that's why we choose it. There could be other material better than that one, but in order to systematically compare, you have to have the same size, same density, then you can make a conclusion. But just say, oh, make a PZT, make this one, this is better than the other one. You know, that's not a very convincing people. To make a good conclusion, we have to do that systematically.
And as a follow-on to that, you showed a periodic table of different members of the Wurtzite family, etc. You speculate as to which one you think might be comparable to zinc oxide in terms of synthesis or in terms of the power output. You know, you show the next 7 years might be these different materials to consider.
Yeah.
Which one of those compounds do you think would be the possible successor to zinc oxide?
Very good question. Thank you. I want to focus on nitrides a little more. The reason I like for nitride a little more is that not only explore the energy conversion part, I want to explore its Piezotronic part, particularly integrate with LED. That's what I want to see. So we need to get a new MOCVD to do that, to grow that. There's another new learning curve for that, but I anticipate to start that work sooner or later. Yeah.
I'd like to ask your vision on this. You know, this is great. How much would this change, let's say, our energy need? You know, this would be cleaner, stuff greener, but would this make a dent in the, you know, the waste we have here, the carbon release and all this?
Good question. This is a big
so
picture.
What do you think? Yeah.
I think at the very beginning, like 7, 8 years ago, we started small. Let's say, okay, let's focus on little sensor system to power this. But today, I think I can look bigger. The reason because we make like our lab, or our lab, your lab too, make a solar cell, we make a little patch like that. Immediately we get some efficiency, we can claim this can contribute to solar energy. And it depends on how do we scale up these things. Scale up this one. Use the line wind. And today wind is fairly severe, so use this wind. Put in plastic, this in plastic, back and forth. That's I can envision as well. So I cannot claim how much we contribute to the total energy, but I have a hope next few years we want to demonstrate something towards this step. Hopefully one day we can contribute a little percentage. Then I'll be very happy. Even we can contribute the power source for the portable electronics. I think there's a big part of that because the power portable electronics is not measured by the price of the power. So let's say you charge a cell phone 50 cents per watt. Say no. If you're 35, I'll charge my cell phone 50 cents. I don't want it. That's not the question, right? For large scope, that's the question. But for the portable electronics, we have to have it. We have to have it, right? Like a pacemaker, need to replace battery. Is $1,000 battery or $2,000 battery? Let's get the best, right? So it's different mentality setting for that.
Very nice. Thanks for work. I'm really interested in active nanosensors. So wondering, do you have elaborate a little bit more about the maybe using that in the biological system where it can do active sensors, and how do you increase the selectivity and then suppress interference?
Oh, okay. Very good question for that. I think for biological sensors, we try to, currently we are being developed like glucose sensors, self-powered glucose sensors use this technology. But so far, we still rely on the, for example, if you have a glucose sensors, you have the specificity, then we can use our Nanogenerator to integrate with yours. And we have not much effort on the develop sensor which have a very good selectivity, like what you did as an expert. So that one, I need to collaborate with you and other people to use your strengths and our strengths to make a system. That's what I'm thinking, yeah, for the biological sensors.
I showed the Nanogenerator driving Broadway with somebody beating on it. Is there any mechanical degradation effect of the generator?
Very good question. We did all kind of tests for this one. We find that we test some of the over million cycle, but we didn't do billion cycle how to stable. But I have one number to offer you. Is we make these nanowires. We want to see, does this have fatigue? So we put this inside a transmission electron microscope. You know, my old area is microscopy. So we put this resin like an angle 7 degrees. We resin this for 35 billion cycles. The student have to watch for a few days, make sure it's resonance. and the conclusion was no fatigue. So from the material itself, when you make a smaller dimension, the mechanical behavior improves gigantically. So through that, I can believe that that's why another major reason why I use nano. People say, why do you choose nano? A box is okay, but look at the mechanical stability, robustness, and flexibility. They give you a large, and also non-linear effect as well.
So following your points, is there a way to
Yes, I didn't show you the picture. We did not only sample, we can have a common substrate. We can grow right on top of that. They become all like a self-assembly. So you don't have to do the unique self-assembly, but grow like that. The reason, let me emphasize this, is that if you do chemical assembly, one nanowire and the other one can reverse in polarity. Because you only geometrically assemble it, but the growth ones keep them all have the same polarity. That's what we need. So if you do self-assembly, it may not work for this purpose, but when you grow at the same time, it's keep the polarity.
So maybe one more final question for our speaker. Their final question. Okay, then we'll conclude the talk. Let's thank our speaker again.
Thank you.